In this video, I'm going to be talking about casting as it relates to the HSC Engineering Studies course. So obviously there's other definitions of casting, like for movies, but we're going to be talking about a variety of different kinds of casting. So in all of our cases, casting is where we deal with molten metal, where metal is heated up to the point that it becomes a liquid, and we allow it to cool and then set. This website here lists 10 different kinds of casting. The Copeland Year 12 book talks about 8. The difference is that one of those is, I think it talks about 9, but it includes ingot casting. So similar to what we see here in this list. The ones, I don't think we talk about vacuum and squeeze. They're that's pretty much the differences. Okay, so if you need to, in Year 11, we talk about 3 specific ones. Let's see. In Year 11, in Volume 1, we talk about sand casting, die casting, and investment casting. But we're going to be talking about all the types of casting discussed in Copeland's Year 12 textbook. So if you have to give an example, particularly in Year 11, I like to ask questions where give an example of a cast product. Garden taps are usually cast. I should have a picture of that. Cast garden taps. So you might see like a brass tap like this. And that's sand cast. And we can see the, I should have done a new image. Hopefully that'll work. Okay, so we can see the pattern on there from the sand on this tap. But we're going to jump ahead, and the other example that most students give is engine blocks are cast. So we're going to look at that example to start off with. So this is a video made from BMW that shows a cast, how they cast the engine block. We're not going to watch it in real time. We're going to skip through. So I don't want to overwhelm you too early on. But in that case, we can see the molten metal being poured in. It's allowed to cool. And we can see the finished product. Well, the end result of that casting process. Okay, so that'll do for the moment, but moving on. Okay, so to start off with, going in the order of the Copeland textbook, first thing we have is ingot casting. This is the idea that often when metal is first produced, when we smelt the metal from its ore or its raw materials, we will often make things into bars or ingots, and so this way they can be transported and sent out. Now, something we need to talk about with casting is we need to talk about the shrinkage zones and some defects and the columnar grains where it cools, those sorts of things. We're going to talk about that later. That may even be in a whole separate video. But for the moment, we're just going to identify different kinds of casting. So first off, ingot casting is a way of producing a amount of clean, homogeneous, so it's all the same material, metal in a bar or another simple shape that can be easily transported and handled. Okay, so these days that's less common. What we're more likely to use is continuous casting, and that's the last one on this list here. So continuous casting is the same idea as making as an ingot, but rather than making one ingot at a time, you have a conveyor belt. The analogy, I guess, could be made, there's similar analogies when you talk about, say, piston engines to jet engines, but the idea is that we could make a cookie one at a time, where we mix up the dough for the cookie, we put it on the baking tray, put the tray into the oven, make one cookie, And then when we're done, we make another cookie and then another cookie. Or maybe we could even put a couple of cookies onto the tray at a time. But the idea here with a continuous process, it's like we have a conveyor belt. So rather than opening and closing the oven and waiting for cookies to be ready, we just have continuous continuous metal, solid metal being forced out of this process. So we just have a continuous run and we can just cut it to whatever length we need. So that's the continuous casting process. Okay, so we've talked about our example. We can now talk to probably the most, this is one of the three that we look at in Year 11, sand casting. So I have quite a few videos on sand casting, but we'll start off with this animation, which I think is, it's not bad.
Is there a difference between regular sand and casting sand?
Excellent question. There is a difference between regular sand and casting sand. This is not the sand that you see on the beach. When we watch some videos, we'll see that the sand is often mixed with a binder, a binding agent that holds it together. It's usually black in color, and we can also, at times, we can dry the sand. We can fire the sand to make it quite hard. It can still be crushed. The sand, when it's not fired, when it's what we call green sand, doesn't mean literally green. It just means that it's soft and it got that binding agent. It can be reused over and over again, whereas a fired piece of sand, it can't be reused. So that process, that animation there, gives us a good idea of what the methodology looks like. So we're going to watch someone doing this in his backyard. This guy has a stack. I think he has dozens of videos on casting, like more than 90. There we go, 103. I'm not saying, oh yeah, they're all metal casting in the backyard foundry. Okay, so in this case, what he's got is two solid objects that are made out of wood. My boss, that when I was in high school and out of uni, that I worked with in residential construction, he started his life as a pattern maker, and so he told me about pattern making, and a lot of things that I didn't really understand when I learned about them from the textbook made a lot more sense when we went and visited a foundry and saw it. But so he used to say that they'd use silky oak. Silky oak was a desirable timber because it was very easy to work with a chisel. And you can see here, so he's got his two pieces, and that's the sand. That black material there is the sand, and it holds its shape pretty well because of the binding agent.
It looks like dirt.
Well, yeah, it does look a bit like dirt. Okay, so he's putting some powder between them. So that's that tube is how he's going to be able to pour the metal into the mold. Now, so the question you might ask is, so that there's two parts of this mold, so the cope and the drag. We're going to learn about that more in the textbook, but there's some terminologies we use. So we also have things like the runner and the riser. So the runner is so that we can pour the metal into the mold, and then the riser is for the overflow. We usually want to add about 25% more metal than we think we need, so that way it gets into all the voids. There are pins, locking pins, that hold the box together so that it doesn't move around, so that we don't have our shape being warped. And so he's compacting that sand. Now, so that's going to be his riser. That tube there is where the excess metal is going to pour out of. Okay, so the question is, how is he going to pour metal into a solid object? Well, do you have any guesses?
Does it like go into the sand?
Well, no. So the metal doesn't pour into the sand, but what happens is that he's going to remove those wooden blocks. But then the thing is, how is the sand going to hold its shape when it's upside down? Why doesn't it fall into the groove? That was the thing I never really understood. When I looked at cross-sectional diagrams, I couldn't understand what's holding the sand up. And the answer is that just the sand is, we'll see that, so he's going to, they call that a gate. So the gate allows the metal to flow from the riser into, he's actually casting two separate objects. It allows the gate to flow in, and he's removing his pattern. So that piece there is called the pattern. And he's using some screws to remove one half of his pattern there. And when he does that on the other side, he can still put the two boxes one on top of the other. Okay, so he's going to use a sand core. So this is how he gets the hollow bit in the middle. So we'll talk more about cores in a second, but that's so that the entire thing doesn't fill up with metal. Yeah. Okay, so this will still hold its shape. Even you can see how it's holding its shape when he's holding it on the side. So that binding agent holds the sand in position, which I guess is kind of like a sandcastle, but it's a little bit better. And we can see he's going to tip it on. So he's going to put the cope upside down, and it's going to hold its shape. And then he's going to pour the molten metal. So he's got a crucible where he's molten pewter, and skipped a little bit to we can break away the sand, and what we're left with is our finished product. Clean it off a little bit to remove the sand. Remember we had a sand core. That sand can be removed. Okay, so that's the first video that we're going to start with. Now, often patterns are made with a lot of technical accuracy. So early engines were made out of wooden patterns. Even space shuttle parts, I would imagine, would have been made with wooden patterns. Don't quote me on that one. But the point is that everything kind of was made from these wooden patterns, and they were made to the precision of the pattern maker. So we can see the same process. He's used that pattern. He's used the same pattern on both sides. So he only needs to use the one pattern twice. Yeah, he's used the one pattern to get both sides because the object's symmetrical. And then he's going to make the sand core. And so the sand core, he's making this box here. So he's filled that up with sand. He's going to release that, and then we've got the sand core. And that sand can be broken away when he wants to clean out the finished product. And he's going to pour in the metal. He's releasing the pins that hold the cope and drag together. We can see the molten object. He's breaking away the sand, and then we can maybe see a little bit of sand in the core, but no, that's been removed. Now, we can see along the side there's a flash line. So that line where we can see where the steel has been poured in, and we can see along the join. And that'll have to be machined to clean that off. Yeah, where the two halves have joined, and the riser and runner, they have to be cleaned off as well. So we can see where the metal's been poured in, that has to be cleaned out as well. Okay, so that's those two. This video here is good because the guy gives a lot of description about the different parts. He names the cope and drag. He talks about how he casts a cylinder. He goes into some detail. So he's using a different coloured sand or a different binding agent to hold the sand together. I won't go into that video because it's fairly long, but he's giving a lot more detail about how he's making his process. What he does do that's interesting at the end is he also uses a die cast method. Now this die cast, normally we think of die cast as being a metal mold, and usually very, very expensive. But what a die cast mold is just means a permanent mold. A mold that you can reuse over and over and over again. A sand cast, you have to make the sand mold each time from off the pattern. Yeah. In this case, we can use a metal pattern or a wooden pattern, but a die cast, the idea is that the mold is permanent. And in this case, the mold that he uses is very simple. He's just using a few pieces of, I guess that's MDF or plywood, that he's probably laser cut, and he's going to pour that in to his mold. And when he removes it, we can see that he has a fairly high degree of accuracy. We can see the lettering from where he's laser cut, and you can see the image that he's cut on the opposite side. So I just thought that was interesting and worth pointing out. Okay, so when we're talking about sand casting, we can see here this process that we can have an asymmetric mold, and in this case here, what we can see is the top half of the mold. This is the sand being poured into the mold with the pattern, so this might be a steel pattern or a wooden pattern. And we can see the bottom half being a different shape and the sand being poured in. And when those two halves of the mold are put together, we can pour the shape. And here's where we can see the effect of the core. So we have a core that allows us to have an area so we can have it doesn't have to be a fully solid object that's being cast. And so that core separates the two molds. It's held in place just by the mold itself, the top and the bottom. Okay, and that gives us our process. Okay, moving on. Okay, I just wanted to show, because I think sand casting is the least intuitive, I think that it's always interesting to look at some other examples. So here we have the two halves of the mold, cavity prepared by patterns. Cores can accommodate holes that can be seen through the bottom half of the mold, which is called the drag. The top half is called the cope. Okay. I'll quickly show you where that's shown in the Copeland book. So we can see that the top half is called the cope, the drag. We can see that the drag is, the shape is originally made upside down and then it's turned upside down to give us the drag. We have a riser and a runner. We pour into the runner and it goes up the riser. Now that sort of detail, that would be I haven't seen that in a HSC question. I wouldn't say it's unreasonable for me to ask that in a Year 11 test, to ask you to label the cope, the drag, the riser, and the runner. That terminology, I think, is reasonable, but I can't recall off the top of my head seeing that sort of detail discussed in the HSC. Here we see some wooden patterns, another wooden pattern that's more complex, and here we have a very large pattern. So I'm not sure if this is, it looks like it's timber, but I can't say for sure. Another complex pattern, just to try and give you the idea of some of the complexity. Okay, so the next one in the Copeland book is shell molding, and the idea here is that a small amount of sand is coated around the outside of a pattern, usually a metal pattern, and we'll have a look at that. So here's an animated example of how that works. So we have, this is actually the second half. So we remove the first half. So we can see the mold being removed off. That mold has been allowed to set on the metal pattern. It's been removed. We're then going to take that away. We're going to make the second half, do that process again. Okay, we then get a core. So we're familiar now with cores, and they give us the void or the hollow in the mold. We can see the riser to allow the metal to flow in. We pour the metal. We can then remove the shell and the core. So that white area is the core. That gives us our finished product. Okay, moving on to the next method is centrifugal casting, and this can be used to cast things like pipes, or it can be used to be able to cast very small things like jewelry. Centrifugal casting can be used for glass as well as metal. So I'm not going to go into too much detail with this. especially for large castings. This is not something I'm as familiar with, so I'm not going to go into too much detail. But the idea is that you can still have a core, so that you get your hollow, or you can just rely on the force, the centripetal force, to hold the metal against the rotating walls. But in this case here, what we're going to look at is using using a centrifuge to produce jewelry. So what we can't see here is, in here we have a mold. It might be a ceramic mold, or it might be a sand mold, probably more likely to be a ceramic mold. And what we're going to do is, the next video might be good. I haven't watched that. So he's heating up just some scrap silver that's, you can see, was just a whole bunch of wires. He's heating that up with a torch, and then once it's molten, it's going to spin. Often this is done in a vacuum to reduce bubbles. And then when it cools, removes the crucible, or releases the crucible, and we can take the ceramic mold, allowing it to cool, and breaking off the mold. And we can see the ring that remains. Okay, to produce that ceramic mold, what you might do is you might 3D print the image that you want these days, and once you've got your shape that you want, I'm not as interested in the 3D printing process. So he's got the ring that he wants. Doesn't look like it shows how they make the mold out of that. Well, we'll see that when we get to investment casting. Okay. So the next one we have is die casting. So die casting is any sort of permanent mold. It's a metal casting process. This one here, so the Wikipedia set definition says 2 steel dies. Okay, so what we're going to look at is look at a couple of animations that show this process. Okay, so we have some molten metal. We have our metal die. The metal is forced into the mold. Now, in this case, the metal would be done under pressure, but it can also be done under gravity. And then the mold is removed. Now, it looks like in this case there's two separate materials that are being made here. So we have the terminologies of tree and sprue. So the idea is that we're casting through this central area, but we have sprues that connect it to each individual item that we're producing. Now, so anyone who's ever played Warhammer, those models, they're made out of a die cut. Well, they used to be made out of. If you buy, you don't get metal pieces anymore, but they used to be metal. They were made out of a die cast process, and they have a flash that needs to be removed. They're now injection molded, but that's a plastic process. That I don't want to confuse that. Injection molding is for plastic. Okay, so we'll just quickly flick back to the textbook where we can see, okay, there's two ways of doing die casting, so permanent mold casting. So we can use gravity or pressure. So I'm not going to go into too much detail in this recording, but this animation here shows how we can use low pressure molding. or low pressure die casting. So we can see that the air is forced in, and the air being forced in forces it changes the equilibrium, which pushes the molten metal up into the cavity. And then the process is the same after that. Okay. So the next one we're going to talk about is investment molding. Now, I mentioned this in my summary of Chapter 4, that investment means to surround. It doesn't mean cost, but it's worth knowing that it is also typically more expensive. So what we're going to do is we're going to take a mold, and the mold could be a wax mold that's been 3D printed, or it could have been produced from another process. And what we're then going to do is we're going to coat it in plaster, so in ceramic. But we can see here just it's a bag of plaster. And we're watching again my Ford boy in his backyard, and he's got his mold that he's not using wax, he's using PLA, which is one of the plastics we've learned about. It's biodegradable and it can be used with a 3D printer. And he's stirring the plaster. He's going to coat the 3D printed objects. You do actually see the 3D printed object a little bit more detail earlier. I just skipped backwards. There you go. That's what it looks like. And he's coating it in plaster. Normally we don't need that much plaster. And to remove it, he is just going to heat it up. And that's going to you can see that it's disappeared. Where'd it go? So it's melted, and it's melted into that tray below. It's a shame that he didn't show it. I was disappointed that he didn't show it. Okay, so we've now can see the cavity, and the cavity can have very, very high level of detail. So we're using green sand, even though it's not green. So that just means sand that hasn't been fired. It's in a binder. And the point is he's going to pour metal into that cavity. The same as he would otherwise. Okay, so he doesn't really need the sand around. It's just for him to work the material. Okay, so we're going to watch that done as an industrial process. We've got this animation. So the first thing is we're going to, in this case, they're molding the wax. So this would be maybe injection molded. So we have our part that we want. We have our tree and sprue. It's coated in ceramic. The ceramic is fired in a kiln, and the wax melts out. It's important to mention that sometimes the thing has to be shaken or rotated in order to get the wax out of areas that might be below the thing. Once it's removed, we can then pour in the molten metal. The molten metal cools. Yeah, there we go, cools. We then shake off the ceramic, and the individuals are cut from the runners. So they can shake or rotate the mold in order to get all the molten wax out.
What would happen to it?
Well, okay, so what would happen if there was wax that was still left in there? There would be a defect, right? So there would be a part missing in the metal, and sometimes that might that's almost certainly going to be a problem. We usually use investment molding for things that need very, very high precision. So it's worth talking about for a Year 11 standard. Where do we use these three different processes: sand, dye, and investment? Pretty much we can say that they move up in the order of precision. So sand is generally cheaper for one or two items. Die casting, it gives a very high level of precision, but you generally need to do a run of 1,000 to make it cost effective. Investment molding is gives us the highest level of precision, and typically we do it for things that are specialty items that need to be a very exacting detail. So maybe in the case of biomedical and innovation or engineering, that if something's made for one patient and it's only going to be used for that one patient, we'd use investment molding because we need it to be perfect. It's also good for things that don't machine well. So because with sand casting and die casting, we're always going to have a line that's left over on the side, the flash. We don't want to have to remove that. So that's the difference. Sand is generally the cheapest, and it's good for small quantities. Die is very high precision, and it only is ever cost effective when we have very large runs. And investment can be used for individual runs, but we use it where we need. We always use it when we need a very high level of accuracy. That's for those three that we talk about in Year 11. To go back a little bit, when we talk about shell molding, where do I get to shell? Way out here. So it has like advantages and disadvantages. It can be automated, so it's good for mass production, and it's, I think, is an intermediate. It gives a medium level of accuracy. It's a little bit more than sand, a little bit less than die. Yeah, I'll leave that there for the definition. What else did we cover? Centrifugal is anything that has good rotational symmetry. So pipes are a good example of where we want to use that. They're good for jewelry, because for jewelry we have very small items where we need to fill the voids completely. So that's the advantage of when we're doing centrifugal process for jewelry. But back to investment casting. So we've just watched the animation, and now we're going to watch this video where what we have is, there we go. I mentioned a tree, and so we've seen the mold, the wax mold, and we're going to see that it gets coated in a ceramic. The ceramic gets dipped and allowed to set. It's then fired in a kiln. And we don't see that being shaken off, unfortunately. And then they're going to fill that with molten metal. Sorry, I said earlier we don't see that being shaken off. What I mean to say is we don't see the lost wax, is what I mean to say. Obviously, if you're interested, you should go back and watch these videos in full to see we're removing the ceramic, and then it's being removed from the tree. And then you get your finished product. There might be some degree of machining afterwards, but the idea is it should be minimal. So what are we on to next? Okay, the last process we're going to talk about is full mold casting, and this process usually uses styrofoam, and in this case we don't remove the mold. So with wax we do have to remove it, but with styrofoam, because styrofoam is something like 98% air, we don't actually need to remove the styrofoam. We just have a small amount of area where the styrofoam will run into when it melts. So let's look at that process. And this is, I think, quite a very good video. It gives a lot of description of the advantages. But yeah, so it's made of polystyrene foam. It's cut away with a CNC machine. So it's CNC is so we produce the polystyrene foam. Filled with sand. We pour the liquid metal in, which causes the foam to evaporate. And we get our finished product. And we can see some really amazing molds that they've used. And then they go on to talk about some of the advantages, disadvantages, how they make the molds using the CNC, which, CNC stands for Computer Numerical Control. So it's just a computer-controlled machine that cuts it away. So we have routers and other milling machines. And it goes through the process in a bit more detail. The sand is removed. All right. Finishing as needed. And that's the finished product. Yeah, look, a little bit of machining. Okay, so I thought that was really interesting. So let's have a look. We talked about that. Okay, so that will do for this video. I might go into a little bit more detail about grain crystallization things. I might splice those two videos together, but I'll see how I go. About grain formation, and I'll start with my my famous joke about what do vegetarian zombies eat? Grains, grain. Anyway, so my favorite cereal is Nutri-Grain. I'm often seen eating Nutri-Grain in the staff room. At the moment in my house, I have 9.5 boxes of Nutri-Grain because I buy it when it's on sale. Then what are we going to look at? So we don't need that window anymore. Okay. The end of last video, I didn't find mass production of centrifugal. I don't know if it's centrifugal or anyway. This casting method, and so I just want to point out that they have this thing on the outside is a core, and they're rotating the metal. This is a pretty good video. I watched this before I started recording, and I like this video. And allowing it to cool. It's nice and red, and there you go. So then the core is removed from the bell. There we go. So never let it be said that I only showed you jewelry. Okay, this window probably didn't need to have open. This is where I have we have a video on properties and grain structure. So we've talked before when we talked about heat treatment about how normalizing causes us to form small grains. Well, we're going to look at the casting process and the kinds of grains that it produces. So I can delete that. Now, if we go to this video here, right at the start, they start by zooming in on some grains. So we've talked before about how zinc has very large grains, and when we look at galvanized structures, we can see the grains quite clearly with our eyes. But this piece of metal, you can't see any grains. But if you turn it around, you can see grains. And then they're going to say, well, okay, with this piece of aluminium, how are we going to see the grains? Well, what we do is we polish it, and then we etch it, and like magic, we're etching it with acid. Oh, look at all them grains. Grains. Okay, but how a grain forms, the video asks. Well, how grains are formed is we have this video where they're going to take some molten, I think this is aluminium, here we go, and they're pouring it in, and we're going to watch these grains form. So when we cast, we've got the molten metal, and we're going to see grains, little baby grains forming. Oh, it's so exciting. Okay, so to start off with, what we have is nucleation points. Nucleation points are I like to think of in, say, like a game of musical chairs, the nucleation points, they're the first atoms to sit down and form crystals. They start holding hands, and then all the other kids start holding hands, until eventually you've got this giant grain. Let's have a look. So we've got nucleation points. They then form into dendrites. Dendrites is Latin for little tree, and they look a little bit like little trees. And then we often get secondary branching. In this case, we can't really see as much secondary branching, but we can see some grains starting to meet, and we have a grain boundary forming at those points where the grains are starting to meet. There's a grain boundary. And they keep growing, the grains keep growing. As they cool, more and more atoms are joining into the crystal lattice until eventually the thing is complete. Now we can see some defects. We can see some slag, some imperfections that have formed, impurities that form in our crystal structure. And that happens in industrial settings as well. So if we go to the Copeland textbook, now this is in the Year 11 textbook, and it's worth pointing out that the numbers go in the wrong order. So it's all you need to do is just cross out the number 3 and replace it with a 1, and they just read left to right. So we have the nucleation points. So that's the first atoms that start to form down. They form the basis of the crystals. We have dendrites grow from those points. Dendrites grow secondary arms, and then where those grain boundaries meet is where we have the grains. Does that make sense? Yeah, you good? Thumbs up? Cool. Okay, so then we're going to look at the grains. Well, okay, so we talked about some imperfections earlier. We talked about or defects. We talked about we can have inclusions, but we can also have something called a pipe. A pipe is where the thing cools too quickly. We're going to look more at those problems in a second, but yeah, I don't really need that. Okay, so we've got here, when we cool down, we have a macro structure. Macro means we can see it with our eyeballs. And when we look at, without a microscope, we can have shrinkage. Often if we just cool things into the air, we'll get shrinkage in the top. But what happens is where the thing cools faster, it makes sense that when you cool faster, you get smaller grains. Yeah, because if they're cooling quickly, there's going to be more nucleation points. When they remember that the crystals grow as they cool, and so if it's cooling quickly, there are going to be more kids who say, "Hey, sit down," and they're going to form those nucleation points that the crystals are going to grow from. So on the outside edge of our mold, that's obviously going to be where the metal is going to cool fastest. So it's going to have very small grains in what we call the chill zone. Then, from the outside of that, what we often get, especially if we're using a metal mold, is we can get columnar, I don't even know how to pronounce this, column-like grains. These column-like grains are because the heat is drawn to the outside, so it gives us long, thin grains. In the inside, where the thing has had more time to cool slowly, it will give us equiax grains because it doesn't really want to go to any one direction. So it's just going to cool slowly and form small grains. This is from Wikipedia. This is just on casting. It actually is a really great page. I should have mentioned this earlier, that it goes into the advantages and disadvantages of sand casting, shell molding, giving a higher finish, investment casting, saying it's a very old method, that it talks about die casting, it talks about centrifugal casting, and continuous casting. So a pretty good page for people looking for more information. It also goes into details on casting defects, which we're going to come back to. Okay, so if we look at this page here, we can see that in this case, we're probably looking down on something that has been made out of metal. And we can see that because they've got a metal wall, we're going to have long column-like grains all the way around and equiax grains in the center. Whereas here, if we have, say, a sand wall, well, because the sand cools slowly, the metal is going to take over and get long column-like grains that are much longer, and they're in both directions, in a north-south shape here. So the metal walls which draw out heat faster, which cause directional column-like grains. Okay, we'll just have a quick look at some pictures that I had available before we move on. So here we can look at the difference between, normally I like to have the picture open up. There's a big picture before I get started. Okay, so we can see these are what the grains look like. In class, I will have shown you some ingots that we have at school, but we can see these long column-like grains, and here we can see equiax grains, and here we can see very small equiax grains. So that gives you an idea. You can close that. Okay, and here again we can see column-like grains to the sides, and here we can see our small equiax grains on the inside. So these are differences in rate of cooling. So yeah, we can make predictions based on, if I tell you that there's going to be a metal wall and a sand wall, we can predict what kind of column growth we have. I would say it's a pretty tough question for a Year 11. For Year 11, I don't think I've seen many HSC questions on this sort of thing, but definitely an interesting question and something that I would say that could be in an exam. Having to label a diagram, and if I say draw a diagram showing sand on all sides, or metal on all sides, or metal on one side, that sort of thing. Okay, so we're then going to talk about defects. Well, so we have shrinkage defects, gas porosity defects, pouring metal defects, and we'll look at those. So here we can see like a blowhole that's caused a defect in our casting. And what I have here is, okay, 21 defects and how to get rid of them. So here you can see 21 defects and what they look like and how we can avoid them. What we're interested in is closed shrinkage defects. So we can see piping, and what the book refers to as secondary piping, they call a macroporosity or a microporosity. So how do we prevent this? Well, this usually happens because of uneven shrinkage. So it means it's cooling unevenly or cooling too quickly. And so we can use things like, we can use cooling ribs to control the temperature distribution. We can also have more injection points. We can have the metal being poured in from different locations, and so that way the metal is going to be entering the mold more evenly, and it's going to have more even temperature. And yeah, this is beyond the scope of the course. I'm not really too concerned about these sorts of things. I would be happy that you can name a primary pipe, a secondary pipe, and an inclusion. So we'll have a look at some of the inclusions we can look at. We can see sand inclusions, slag inclusions, and how they can create problems in our materials. So here, it's important to see that this area here, this grey on the left, shows a slag inclusion. So it could be the ingot on the left shows a primary pipe in the top, which is formed as the metal solidifies, the grey segregation of impurities which exist in the material. So it could be, it could just be gunk that was on the side of the mold,